So as I mentioned while we were programming, or at the end of programming, we have to find a way to fixture this thing. As you can see, we have it sitting in a vise back here. It's just a standard traditional vise. But when we do 5-axis machining, traditionally we like to hold it in a special vise that uses a dovetail to grab the part. The advantages of that are that the part is actually sticking up out of the vise as much as possible. It keeps the jaws out of the way so that we have access to all 5 faces of that part. So what I'm going to do is I'm going to begin by finding the center of this part, because that's the dovetail program that I have in this machine. We're also using a different type of programming for this dovetail operation, which I'll show you here in a minute. What I'm going to do is I'm going to find the center, and I'm going to zoom in and I'm going to show you how I do that using this traditional method. We're going to use a different method with probing when we go to do the part and we actually go to machine the actual part out. Here I'm using what we call an edge finder. It has a little tip on it that is spring loaded, and it kind of wobbles around. But once we come up to a side, it'll actually spin true, and then when we're right on that edge, it'll kick off to one side. You'll be able to see this when we do it on the front face. So what I'm going to do is I'm going to do the front face first, and I'll do the other sides, and through the magic of video editing, we'll find the center of this part, and you'll be able to see it machine the dovetail. Alright, I'm going to start the machine up. So our spindle is moving, and now I'm just going to use my handle jog to jog this into position. Of course, I got to jog down in front of the part, and I'm going to overhang that edge finder just a little bit. I'm going to reduce my speed, and I'm going to come in and find this edge. And this may be a process that many of you are familiar with. You can see right here, it's spinning true, and then all of a sudden, it kicks off to one side. So I'm going to bring my Z up, and I'm going to store this location. Now, traditionally, what you probably will do is you'll probably move this over 100 thousandths to compensate for the width of the edge finder, half the width of the edge finder, so that the center of your spindle is in line with the edge. We're not doing that for this because we're going to find both sides, and then we're going to find the center. So if we're off by 100 thousandths on the front face and 100 thousandths on the back face, it doesn't matter. Dividing that by 2 is still going to give us the center. So really offsetting it, that 100 thousandths, is just a waste of time in this procedure. But if I did want to find this edge, I would definitely need to offset my 100 thousandths. So I'm going to go ahead and continue that for the other side. We're going to find this side, and I'm going to store that location as well once I find it. Going in. Oop. And right there's that edge. So I'll just store that one. And then I'll do the math and I'll figure out the center. I'm going to do the same thing with the X. Alright, so I found both sides of the X and I found both sides of the Y. I did my math. I set my G67, which is my fixture offset. Now I'm just going to test it. I'm going to send it to that location, and we're going to see if it looks like it's in the center. So I'm just going to type in a G90, G57, X0, Y0, G0. And we're going to run that. And I would say that looks pretty good. Looks like it's right in the center of the part. So we are just about ready to run here. The next thing I need to do here is I need to set my tool heights. So I'm going to use a 1, 2, 3 block. And I'm going to bring my tools down. And I actually take them below this 1, 2, 3 block. A little bit there where it can't go under. And then I'll slowly bring it up until it fits under there. And then I'll set my tool in my offset page. Once I have those tools set up, now I need to find out where the height of my block is. And there's a couple ways you can do this. You can use a piece of paper and just come down until the paper gets tight underneath the part, which is right there. rips the paper. That gets me to about 3/1000ths. Piece of paper is usually about 3/1000ths thick, so I can compensate for that. The other way is if you're losing aluminum, a lot of times what I'll do is I'll hand jog the spindle, and I'll come down until I scrape. And right there I've scraped the part, so I'll just call that 0. And I'll set my work offset at that point right there. Okay, so now what we're going to do is we're going to enter our G65 as we discussed, and we're going to need to enter those variables because we need to give it some information. So I'm going to start by hitting G65, and it looks like my first variable here, of course I have this stuff written down, is my X value, which is the dimension of our part in X. Well, I know that that's about 4 1/8, so I'm just going to make it 4.2. I make it a little bit longer just to make sure that it machines past. Y, which is our dimension in the Y-axis, that's going to be 3.5, so I'm going to make it 3.6. W, which is the width of our dovetail feature, so I'm going to make this W 1.75. The depth of our dovetail, which is, we're going to make, which is D value, we're going to make that 0.13. The T value, which is the roughing tool number, that's going to be tool 31, so we're going to make that T31. And of course you can't see any of this right now, so I just hit enter, and let me hit T31, I gotta add a decimal point to that. T31 point, alter. So I just hit enter so you can see some of the stuff that I was entering a while. So now I can enter the rest. U, which is our dovetail cutter number, that's going to be U30 point. M, which is what material we're using, 1 for aluminum, 2 for steel. We're doing 2, or we're doing 1. We're doing steel. So we're going to do M 1 point. And E, which is our fixture offset, E57. I for internal or external dovetail. So are we going to make an internal or external dovetail, which I'll kind of show you the difference between once we get over to the machine and start machining some stuff. In this case, we're going to make an internal one, so internal equals 1, so I'm going to make it an I1. And we need a facing depth. Facing depth, we're just going to make that maybe 10 thousandths, 15 thousandths. So I'm going to just F 0.015. I accidentally made a mistake there. And we need our step over for our facing, and it's in percentage. So I'm going to say step over S is actually check that, not 0.75, it's 75 point, enter. Okay. And there you can see all our variables, our G65. Remember, our G65 is what calls up this subprogram that we looked at. And all of these variables are what relay the information that it needs to correctly execute this subprogram. So now that we have our program in MDI, and we're going to call up that 9005 program with a G65, we're ready to run. So I'm going to go ahead and hit cycle start. One thing that I will note is that traditionally I would be running coolant with this machine, but since we're making this video, I turned the coolant off, and we should be okay without the coolant since we're not cutting too fast. So what you can see here is it's doing the facing pass, so we're getting a nice smooth surface on the top here, and it's going to face this off, and then we're going to move into cutting the groove for the dovetail, and then finally we'll cut the dovetail. remember here is this is a macro program. So this will execute a dovetail on any part, any size. All you need to do is put in those parameters. That's what's fantastic about using macro programming. It's going to go change the tool, come down, and it's going to use our dovetail cutter, and it's going to undercut that edge there. Sounds like it's starting to glow up a little bit just because of the fact that we're not using coolant. But that's what you heard with that popping. But when we open it up, you can see here, we have a perfectly dovetailed part. Alright, so here we are in front of the 5-axis trunnion. This machine here has 5 axes, so it can go this way, which is our x-axis. It can go back and forth, which is our y-axis. It can also, the head can come down, that's our z-axis. Then this whole part right here actually can swivel back and forth, which is our a-axis. And the part can also spin around like this, which is our C-axis. Just to kind of demonstrate that for you, I can move these axes. So that's our X-axis, our Y-axis, back and forth, our Z-axis, of course, is over here. You can kind of see that, it's almost out of the frame there, but you can still see it. And our A-axis, which is this one, this allows it to tilt. And our C-axis, which allows us to spin the part around. And you'll see all of these axes actually moving at some point during this program. So let's go ahead and run it. Alright, so what I did was I turned down the sound here so that I can narrate this a little bit. And what we're doing is right now it's going to find the center of the part. And this is what I was talking about when I meant we're going to find it a different way. So what we're using here is what's called a wireless intuitive probing. And that wireless intuitive probing basically just comes down, touches the part, finds the edge, and it automatically records everything into the machine. And then the machine, you can program it so that it will automatically set our work offset to the very center of the part, and it will do that for every part. That way you make sure that you have the exact center of every single part, and it doesn't really matter if it's off a little bit. You don't have to locate the part exactly the same. It has to be close, but it doesn't have to be exactly where it was every single time or where it was the time before. Next, as we programmed it, as you saw from the program, we are facing the part, so we're facing the top here, and this is a messy job. You have a large diameter cutter, so you can see that it splashes the coolant all over the place. And I am toggling the coolant on and off here a couple times maybe, but if we want to achieve a really nice surface finish, you really have to leave that on. So I kind of had to leave it on, and then after this is done, I go in and I clean off the camera, and I go ahead and start it up again so that you can see it without coolant for the most of the rest of the run. But I'm going to go ahead and let this, or basically increase the speed of this video so you don't have to watch it in real time. It'll actually speed up and you'll be able to see everything that's going on, but it'll just move a little faster. Alright, so now we're changing over to our engraving tool, which is a 60-degree included angle, and it has a 1/1000th tip on it. So the diameter of the very tip is 1/1000th of an inch. And this is where I toggle the coolant on and off, so you can kind of see what's going on, but I give it a splash of coolant to maybe wash it off and just keep a little bit of coolant laying on the top. Since we're not cutting a lot of material, it doesn't need to be flooded with coolant the way that it is now. So hopefully here any second, I should be toggling that off, and you'll be able to see most of what's going on in terms of how it's engraving it and all that. So I'll let that play for a little bit in slow motion, or in normal speed, I should say, and then I'll speed this up as well, because this is the part of the program that takes the longest. And that makes sense since we looked at the program and we saw that the longest part of the program is the actual engraving. It has the most lines of code involved in it. So as you can see right now, it's actually engraving the Hempfield, and after that it'll start to move to the shield, the Celtic shield, and then it'll go on to the Thaddeus Stevens part. All right, so what we're doing now is we're going to do a tool change, and I made a change to the program that we created together. And what I did was, for the windows in the tower of the Thaddeus Stevens logo, I actually roughed those out to kind of give it more of a three-dimensional feel. So I made that small change, and that's what it's doing now. It actually pulled up our engraving tool that has a 30 thousandths tip on it. So it's stepping over and it's just roughing that out. And you can see it did that really, really quick. There wasn't a lot of material to remove from them, so that went really quick. Now what we're going to do is we're going to turn back, or go back to the 1,000th tip, and we're going to use that one to go ahead and go back and finish those windows to make sure that we get those corners out of the windows. So what I'm going to do is I'm going to fast forward that, and we'll increase the speed of this, and then I'll come back after it does some more roughing. So it just finished roughing the H, the micrometer, and the book. And you can kind of see that a little bit in the video. It's very hard to pick up that kind of detail. With the camera, we can't zoom in quite as far as we'd like to, and you can't really control the zoom on the camera. But it's going to come back in now with the finish tool, and it's going to take the corners out of the H, the micrometer, and the book. So it's going to make them look, nice and tight. The letters are going to look really smooth. We just finished up with the finishing tool, the 1000th tip engraving tool. So the letters should look really crisp, all the lines should be really tight, the corners should be out of those. So now we can move on to the drill, and this is our 3/8 drill. And I do toggle this on and off so you can kind of see the speed at which we're drilling, which this isn't the fastest we could drill. We could certainly go faster, but this is not a super high quality drill. It's just a standard twist drill, maybe a little shorter than your average twist drill. I am holding it in a collet, and the reason I'm holding it in the collet is because of concentricity. I don't like them to spin out of concentricity because what you'll do is you'll get a lot of vibration in your part, and you won't get as good of a finish in your hole. You could also drill your hole oversize. So that's the reason I hold them in collets. And I do that a lot just to avoid any possible problems. Would I need to? Probably not. I could hold it in a drill chuck if I needed to. Once this drill finishes, and it's almost finished, it's drilling its last hole right now, we are going to go and grab our chamfer mill, and we're going to start to chamfer this thing. One of the things you may have noticed is the whole trunnion, the table moves out of the way when it goes to do a tool change. The reason for that is if you have a long tool, you don't want that trunnion sticking up, and you don't want the tool change to, maybe smack the tool into the trunnion or something like that. So it's basically a safety feature. You have to be really careful with these 5-axis machines. They are much more efficient, but they're also more delicate because they have more axes of movement. So you try to avoid as much as possible crashing them in any way, shape, or form. So right there you can see that it is, it just chamfered the top edge and then it chamfered the holes. So we put a little bit heavier chamfer on the holes, if you remember. Now it's going and it's doing the back side. And I did cut that edge that it's cutting out of the program when I programmed it for this video, but I actually went back and reprogrammed some things and I didn't cut it out on that one. So right now we have 2 more edges to chamfer. This edge here, and then we have the left side edge as well. And then that will wrap up this part, or this cycle. That is officially a complete part. And you can see it down there in the lower right hand portion of your screen. I'm actually going to jog it out into the middle here so you can get a little bit of a better view of it, and I'm going to spin it around for you with the C axis. So as I spin it here, you can kind of see all the sides. You can see the obviously the difference with making sure that we face milled all of the faces. It's a lot more shiny, looks a lot nicer. All the edges are completely broken on it, with the exception, of course, of the bottom, which we're going to go over to another machine and we're going to mill that off and throw a chamfer on there. So let's go ahead and head over to that machine. Okay, so welcome over to our VF2. This is just a standard 3-axis machine, and as you can see, I already have the part in there. I didn't bother going through the setup. It's pretty straightforward. What this is going to do, it's going to come in and we're going to mill off the bottom. I think we're taking somewhere around 3/4, actually no, we're taking about 1/2 of an inch off the bottom because it was 3.5 and we didn't cut really much off the top. So there's about 1/2 inch to take. So it's going to cut 2/4 inch passes here. And you can see I'm stepping over, I'm not taking these all at once. Number one, my tool isn't wide enough to do that. And number two, it really just probably doesn't, it couldn't handle it. It's a lot to take off for a 1/4 inch depth of cut. I believe now it is taking a finish pass so that we get a nice finish on there. Which you can see, as it did in the 5-axis machine, creates quite a mist in the machine just because of the cutter atomizing the liquid. And now we're grabbing our chamfer tool and we're going to come down and we're going to put a chamfer around this part. And then we have a complete part. So, all said, this process took us about an hour and a half on film. So the whole thing, realistically, this obviously was edited, probably took about 3 hours from start to finish to program it and to finish machine it. So if you have any questions or any kind of comments, please leave them below in the comments section, and if I can, I'll get back to you with answers. Thank you for joining us on this collaboration, and I hope to do quite a few more in the future.